Thank you to Raycon for supporting PBS. Scientists have been slowly extending the periodic table one element at a time, pushing to higher and higher masses, and have discovered some pretty incredibly useful materials along the way. But the elements at the current end of the table are so unstable that they decay almost as soon as they're created in our particle accelerators. Have we reached the end of the line for discoverable elements? There are new rows of the periodic table to unlock, and more stable versions of known heavy elements to synthesize. And while our accelerators are coming up short, astronomers have found a strange cosmic phenomenon that may populate the periodic table beyond our wildest dreams. A little while ago we talked about the island of stability, the patch of the periodic table where nuclear physics tells us that we may find new heavy elements of unusual stability, and perhaps with unusual and useful properties. In that episode we stopped short of talking about how to actually make these things. In fact, it turns out it may be next to impossible, at least with current methods of smashing nuclei together, but astrophysicists, of all people, may have found a way to create elements in the island of stability. Instead of building a large nucleus from smaller ones, how about taking two atomic nuclei the size of cities and smash them together and see what comes out? Sounds impractical, but the universe does this pretty regularly with neutron star mergers. Today, we're going to see how this phenomenon may allow us to prove the existence of the island of stability, and how new techniques in the lab are pushing the far end of the periodic table. Before we can fix the problem, let's talk about the problem itself: nuclear instability. So, a nucleus is basically a balancing act between the repulsive force between protons trying to blow the nucleus apart via the electrostatic or Coulomb force, and both protons and neutrons sticking together via the strong nuclear force. This is why neutrons are important. They ensure protons don't get so close together that the repulsive tendencies overwhelm the attractive strong force. For many of the most common elements in the universe, the most stable form is when neutron number equals proton number, like helium-4, carbon-12, oxygen-16, and magnesium-24. By the way, these numbers are atomic mass numbers, and they represent the total number of nucleons, protons plus neutrons. They designate the isotope of the named element. The element is defined by just the atomic number, the number of protons, and each element can have different isotopes, different numbers of neutrons. For the lighter elements, neutrons and proton numbers are often similar, but the repulsive Coulomb force grows quickly as we add protons. The further we go along the periodic table, the more neutrons we need as the padding between the protons to dampen that repulsive force. For example, iron 56 has 4 more neutrons than protons, gold 179 has 21 more neutrons than protons, and lead 208 has a neutron excess of 44. Beyond a certain total number of nucleons, it becomes impossible for the short-range strong nuclear force to hold the nucleus together against the enormous Coulomb repulsion. The heaviest truly stable element is lead 208, with its 82 protons and 126 neutrons. Part of what makes lead 208 special is that it is doubly magic. Nucleons in the nucleus are not little balls held together like glue like we see in our textbooks. They're fully quantum mechanical objects that occupy shells the same way that electron orbitals do. And just with electron orbitals, these nuclear shells are more stable when properly filled up with magic numbers of protons or neutrons, as is the case with lead 208. Without full nuclear shells, an element is more susceptible to radioactive decay. But beyond lead 208, even full nuclear shells can't save these overstuffed nuclei. At some point, excess repulsive force between the protons causes it to fall apart. In the most unstable cases, it splits into 2 smaller nuclei in what we call spontaneous fission. More commonly, the decay is via the emission of an alpha particle, which is the same thing as a helium-4 nucleus, 2 protons, 2 neutrons, or a beta particle, which is just an electron being spat out to turn a neutron into a proton. All elements beyond lead are radioactive and eventually decay this way. And the larger the nucleus, the quicker this is likely to happen. Some of these radioactive elements decay slowly enough that we still find them in Earth's crust, albeit diminished in quantity from when they were forged in supernova explosions and the like. Other naturally occurring radioactive elements are the decay products of more massive nuclei, or are created when stable nuclei are hit with cosmic rays. But some nuclei are so short-lived that we never find them in nature. These we have to make in labs by smacking our more stable nuclei with alpha particles or neutrons to build up to higher atomic numbers. That's allowed us to crack the 100 mark in number of protons to what we call the super heavy elements. But to get all the way up to the current heaviest known elements, currently organesson, with atomic number 118, we just can't build them up slowly. That's because nuclei this large decay quicker than we can add neutrons or alpha particles. Instead, these are made by smacking two smaller particles together. For example, organesson was first made by smashing calcium nuclei into californium atoms quite a lot of times to get even a barely detectable amount of organesson. By the way, calcium-48 has been a go-to for this sort of element building because it also has doubly magic-filled nuclear shells. Very recent work by scientists at Berkeley Lab have used titanium-50 instead, which greatly increases the yield of super heavy elements, and the researchers have their eyes set on the next row of the periodic table, in particular the as yet unnamed element 120. But these new elements are going to be extremely unstable, just as the current super heavies are. For one thing, the versions of these elements that we create with current methods don't have enough neutrons. Remember that the ideal ratio of neutrons to protons increases with atomic number. That means smashing two lighter elements together will always give you an isotope of the new heavy element with a similar neutron to proton ratio as the lighter elements that went in. In other words, without enough neutrons. We could try bombarding the new element with a beam of neutrons to supplement, but it's very difficult to do that before the unstable isotope decays. And there's extra impetus to hit that neutron to proton sweet spot, and that's to reach a new doubly magic region of the periodic table, similar to lead-208 and calcium-48. And this is the theoretical island of stability, which is thought to exist at around atomic number 110 to 114, elements from darmstadtium to flerovium. But for isotopes of these elements with around 180 neutrons. The versions of these elements that we've created so far are at least 10 neutrons short of this, and so they have half-lives between milliseconds and minutes. While the stable isotopes in the island of stability may have half-lives of at least hours, but perhaps up to a few years. It's not yet known whether we can make island of stability elements with particle accelerators, but there may be another way to at least prove their existence. In the past, when our accelerators haven't been up to the job, we've turned to the universe. For example, the most energetic cosmic rays have vastly more punch than anything the Large Hadron Collider could produce. Well, it turns out that there's one phenomenon, that can potentially create island of stability elements, and that is neutron star mergers. Neutron stars are basically city-sized atomic nuclei with the masses of stars. These are the end states of the cores of massive stars after their explosive deaths, when all of that central matter collapses under gravity and is converted to almost pure neutrons at nuclear densities. When two neutron stars find each other, perhaps because their progenitor stars were binary partners, then they'll eventually spiral towards each other and merge. From Earth, we see these mergers as, at first, a wash of gravitational waves immediately followed by a brief gamma-ray burst, and then a longer-lasting kilonova explosion, which I'll come back to. Perhaps the most important outcome of neutron star mergers is that we now believe that they are one of the key sources of heavy elements in the universe. When they impact, huge quantities of neutron matter are sprayed into the surrounding space. Free from the extreme pressure of the interior of the neutron star, many neutrons decay into protons and electrons, forming light atomic nuclei. But these nuclei find themselves swimming in a thick soup of fast-moving neutrons, which can quickly build the nuclei up via the R process, or rapid neutron capture process. Calculations show that this produces elements all the way up to the end of the naturally occurring periodic table. We now believe that neutron star collisions are essential to making many of the heavy elements that we see on Earth, from gold to uranium. As the collided neutron star settles down into either a much larger neutron star or more likely a black hole, the explosion of new heavy elements spreads outwards. Lots of ridiculously radioactive new elements will be in that cloud, and these will quickly alpha decay, beta decay, or fission their way back to more stable nuclei. Because of the extreme abundance of neutrons, there's no reason that elements in the island of stability, or even heavier, shouldn't be produced. In fact, if these ridiculously heavy elements are made, then we would expect them to undergo a chain of rapid decays until they hit the island of stability, and there the decay chain would stall for hours to years, depending, and in that semi-stable region they might be detectable, as I'll come back to. Okay, this is all pretty speculative, but let's look at some actual observations and evidence. So the first neutron star merger was observed in 2017, simultaneously spotted as a gravitational wave signal and as a gamma ray burst. GW 170817 was then observed as a kilonova, a long-lasting glow of radiation as all of the radioactive byproducts of the merger decayed. That kilonova gave us evidence that neutron star mergers do at least produce some of the heavy elements. Before we get to the more speculative ideas of what these kilonovae can potentially tell us as we see more of them, let's look at some more real evidence. Evidence that elements heavier than uranium, so-called transuranics, are produced in neutron star mergers. So stars that formed early in the universe are expected to have relatively few heavy elements because there haven't been many prior generations of stars to make those elements. But such an otherwise unpolluted star that formed shortly after a neutron star merger in the early universe should bear the particular elemental signature of that explosion's debris. These stars give us our current best picture of what exact elements are produced in neutron star mergers. Many of these stars are actually still around, orbiting the Milky Way, and we discover them through the unusual combination of elements seen in their spectra. Now, we can't directly detect any super heavy elements in these stars. Remember, these are stars formed near the beginning of the universe, and so those unstable elements have long since decayed. However, we can look for an excess of the stable decay products of those heavy elements: ruthenium, rhodium, palladium, and silver. And we have found cases of high abundances of these decay products, suggesting that neutron star mergers forged large amounts of elements like californium, a transuranic that's a few ticks up the periodic table from uranium. We haven't yet pinned down similar evidence for island of stability elements, but perhaps by finding more of these ancient stars stained by neutron star mergers, we will be able to do so. But there is hope of observing island isotopes a little more directly. I mentioned that after a neutron star merger, there's this thing called a kilonova, the fading afterglow of light from the decay of radioactive nuclei. Well, if extremely heavy nuclei decay through the island of stability, we might expect that to be reflected in the way the kilonova fades. The way a kilonova changes in brightness definitely reflects the half-lives of lighter radioactive isotopes. For example, there's a brightness bump peaking at around 100 days that's driven by the decay of isotopes in the actinide series that have half-lives in that range. The island of stability elements have half-lives ranging from hours to years, and it's speculated that the quicker decayed elements in that range might leave a detectable bump in the first several hours after a kilonova begins. In order to detect this, we'd have to catch the kilonova as soon as possible, really right after we spot the gravitational waves from the merger. But we've only observed one highly resolved kilonova, again from GW 170817, and it took astronomers 11 hours to find the electromagnetic source after LIGO caught the gravitational wave signal. By then, any very massive nuclei would have decayed already, so we missed any transition in the rate of fading caused by the island of stability, if that transition happened at all. And it's not clear that these magic island elements can even be produced this way. Our nuclear physics tells us that the heaviest elements produced in the R process after the neutrons run out should have proton numbers of around 100 and neutron numbers of around 200. If a dozenish of those neutrons then beta decay into protons, then it's possible these could wind up as island of stability elements. But each beta decay creates an unstable isotope of a new element, and if any of those have a high probability of fission, then the nucleus will break apart before making it to the island of stability. But if we're lucky and the nucleus doesn't just fall apart during that chain of beta decay, then neutron star mergers could produce enormous numbers of nuclei in the island of stability. We just need to catch a kilonova quickly enough. Usually it's our labs here on Earth that help us understand what we're seeing out there in the universe. But perhaps now we astrophysicists can give back a little by proving that the island of stability exists. Then our labs can get on with making those elements. Perhaps we'll do it with the very next neutron star merger and the resulting cascade of radioactive decay shining at us from distant parts of space-time. Thank you to Raycon for supporting PBS. If you want deep focus when you're watching space-time or doing the math for your world-changing theory of everything, you probably want to tune out the noise around you. That's why I want to tell you about Raycon's everyday earbuds, which now feature active noise cancellation. Coming in 4 unique colours, these noise-cancelling earbuds come with touch controls that allow you to choose one of 3 sound profiles. The pure sound profile is attuned for podcast or audiobooks, which is helpful if you need to listen to a refresher lecture on gravitons. Raycon also offers a 30-day happiness guarantee, so click the link in the description box or go to buyraycon.com/spacetime to get 20 to 40% off your Raycon purchase plus free shipping.